Welcome to episode 1.3 of the Groundwater Management Model tutorial series. Here we'll look at head difference constraints as an additional type of constraint and look at some formulations for plume control using those constraint types. So it's often of interest to control flow direction, and that can be done at least approximately by imposing constraints on differences in heads. So for example, if we have in a plan view here, if we have two locations A and B, we can impose a requirement that the head at location A, as a function of our decision variables, minus the head at location B is greater than some specified head difference. Obviously this means that the head at A is going to be larger than the head at B, and therefore the flow direction will be generally from A to B. Now, a problem with this formula, with this kind of constraint, is that it's a very loose definition of direction. So either of these directions indicated on this cartoon would satisfy this constraint. In fact, any head difference that falls into the half plane between that bisects the line between A and B at A could satisfy the constraint if the head difference is sufficient. It is possible to use multiple head difference constraints as indicated here, where we have 3 points, A, B, and C, where we are imposing constraints. And as you can see, if we satisfy both of those simultaneously, we limit the range of possible directions for the flow. It's also useful, this particular type of constraint is also useful in vertical flow control. So I might want to induce an upward gradient or a downward gradient, as the case may be, and I can do so by using this head difference form. So next we'll look at a problem in which we will use these constraints, and this is a capture zone problem. So here we have a plume of contaminant indicated by this outline here, and we have 5 wells, and we'd like to pump those wells in such a way as to produce a capture zone to capture the plume, and we want to do this at minimum cost. So once again we'll impose constraints. I'm going to pick a set of pairs of locations as indicated by the arrows here, 4 pairs, 8 locations total, and make the requirements as indicated in the list of constraints. So the head at location 2 has to be greater than the head at location 1 by a specified difference, which will induce a flow generally in the from location 2 to location 1. And similarly, an upward gradient between pairs 4, 3, 6, 5, and 7, 8, generally upward. In this case, I have the heads depend on the set of decision variables, which are 5 steady-state pumping rates at each of the 5 wells. So those are my constraints for the problem. I need an objective function. The intention is to minimize cost, and a often reasonable approximation for that is to simply minimize pumping, assuming that pumping costs themselves and also treatment costs are proportional to the total flow removed from the subsurface. I've added here a coefficient, which may imply some weighting amongst the 5 wells for whatever, for some technical reason with respect to the treatment system. So the alphas would be assumed known. So here's the complete formulation then. Once again, we're minimizing an objective by choice of the decision variables, subject to these constraints on head difference. And presuming that the constraints are sufficient in number and are properly placed, we would presume that the heads would, the pumping rather, would produce heads that would induce a capture zone for this particular plume. I'd like to go to now turn to a field application of just this sort of formulation. This is a site in New Jersey in the United States. It's a former chemical manufacturing site. The facility is here. Note the scale, it's quite a large site. There's a river running adjacent to the site, which is the discharge for much of the groundwater and much of the plume, which is indicated by the shaded area. This site and the application of management models was described in the paper noted here. The remedial design setup for this site involved a ModFlow-based simulation model, the imposition of gradient constraints or head difference constraints indicated by the arrows. So wherever there's an arrow, we required that the head at the upside end of the arrow be greater than the head at the downside end of the arrow by a certain difference to induce a capture zone. We also impose that vertically at many locations, which are not shown here. What is shown by the X's and pluses are extraction points, potential extraction points, candidate well locations, and also candidate recharge locations. In this particular site, the intention was to design a system where the water would be extracted from amongst these wells in order to produce a capture zone, treated, and then recharged in some proportion at these various locations in constructed recharge basins. The overall problem was about 300 candidate extraction and recharge locations, 600 hydraulic control constraints, and as you see on the screen, the result was infeasible. An important and useful result. In this case, it turned out that it was simply impossible to recharge the water in these two locations and at the same time generate the capture that was necessary. As described in this publication, this produced a process in which the parties involved negotiated on the constraints, and the constraints of the problem, the formulation of the problem, was adjusted until a feasible solution was determined. Indeed, we concluded that the optimization problem was particularly useful because it found an infeasible solution. It would have been, using trial and error alone, very difficult to conclude that there was no possible way to do this. And using the optimization, we could, in fact, reach that conclusion and then adjust the constraints in such a way as to ultimately arrive at a feasible solution. In future episodes, we'll look at how the optimization algorithm works and how it produces these sorts of results.